z is equal to f of x and y. Now we can extend this to 3, 4 infinite variable functions even. And mathematicians, yes, there's a such thing as infinite dimensional functions. Okay, now, but let's just do the 2, because then we can see. This was the picture from yesterday. And if we have an equation of a tangent plane, that much, that this corner, from this corner to that corner, so x changes by a little bit, we'll call that dx, y changes by a little bit, dy, so we are moving from this corner to that diagonal end corner, and your function will go up, right, accordingly. So that change of our function surface is called delta z, and we can approximate that with dz, which is a change elevation of the plane. But if we take a limit as delta x and delta y, both approaching 0, then this becomes infinitesimal and they become the same thing. That's the whole idea. So far, so good. Now, so we said yesterday dz is equal to the partial derivative with respect to z. And then we have dx. Then we have a partial derivative with respect to, oh, did I write z again? Oh my God, I'm definitely losing it. X, and this is y, and then we wrote dy. So far, so good. Okay, guess what I'm about to do now? What I'm about to do is this. I'm going to divide both sides by dt to take a derivative. What is dz over dt? But we don't even know what dt is, so what does that mean? Okay, so picture-wise, this is what's going on. If we take some kind of a vector function, so now we have a vector function. Where do I want to draw it? I'm going to bring this thing lower a little bit. So say there is a vector function R. I'm going to do the vector function in red. So we have R of t, which of course is x as a function of ti vector plus y as a function of t j vector. So far, so good. Now, this is a two-dimensional vector function, which is in our domain. And let's say our vector function moves along this curve like that. So this curve is R of t. You get it? So far, so good. Now, if we erect some kind of picket fence along the top, and then this part, I'm going to draw it only here, this part and that part will have some kind of curve that cuts this surface. You know what I'm saying? Actually, I don't like this curve, is a little ugly, so I'm going to put it prettier. Let's say this thing will go maybe like that. Good. Now, what's the derivative of that thingy? You know what I'm saying? So this is the whole idea, right? Slope of that curve right there along this, on top, above this curve. So that's, in a way, this is x like an x-axis, little curvy x-axis, and that's your y, the function. So that's just simply is dividing. Did I write z? Oh my God. So partial z over partial x times dx dt. You get it? Derivative of this thingy. You multiply it. And plus partial z of partial y dy dt is how the chain rule works out. Okay, so far it makes no sense whatsoever, correct? Yeah, I expected as much. Okay, let's take a concrete example, okay? Example is this. We have z is equal to, computer's frozen. we have z is equal to 2x squared plus y squared. What do you see? Do you see a paraboloid? Well, in case you don't see it, I got this. Okay. So z is equal to 2x squared plus y squared. So here you have it, paraboloid. Okay. Gonna make it. How's that? Maybe I like checkers too much. Okay. Now I'm going to introduce a vector function. Okay. My vector function here is r of t is equal to cosine t I vector plus sine t j vector. Okay. Now another way of saying that is just x is equal to cosine t and y is equal to sine t. I mean, your book probably puts it like that. Okay. Now there's a parenthesis here. Let's see what that looks like before we take a derivative, dz dt. Okay. So what that looks like is I'm going to introduce a vector function here now. Okay, so that thingy, two-dimensional vector. I think I'm not sure if this will work. Let's try it. Cosine t and sine t. That doesn't work, so I have to have a three-dimensional vector. Okay. This is equal to three-dimensional vector cosine t, sine t, and this. Oh, actually, that's not going to work either. Okay, I'm going to use something called the parametric surface. This you don't know what it is yet, but just okay. I have a little bit of thingy here. Now I'm going to vary my u to from 0 to 2 pi. 7 will do. So I have this little cylinder that I'm putting around, and I'm going to have to vary my v. Where's my v? Where's my v? There. Oh, there's a v. And v can go quite high, let's say 10. Now I've inserted cylinder inside, okay? Let's change the color of, oh, should we have actually full rainbow? It's okay, right? Now, do you see, actually I don't want to use rain, I'm gonna leave it for now. Do you see that fact? So this curve that I'm describing is the top of this thingy, you know what I'm saying? Good. So I don't mean entire surface, but I only want the cross section of this thingy, which will be this wavy thingy, right? You with me? Now I want to take a derivative of that thing. And then do you expect some kind of sinusoidal function? Let's see the picture again. You know, up and down, right? So you see some kind of sinusoidal function. That's what we. Okay, so let's do this. So we have the derivative dz over dt, and it is d, not partial, because see, z is a function of x and y, but x and y is a function of t. So this whole thing is a function of t. You know what I'm saying? If I substitute both of this, then the whole thing becomes a function of t. You get it? So it's kind of like a chain rule last year, except there are two inside functions. You know what I'm saying? And the picture-wise is what it is that we just saw. So this is equal to, so computers really misbehaving. Okay, right. First, partial z, partial x, dx, dt. I'm just rewriting the formula. plus partial z, partial y, dy dt. So you have to do it for both x and y variables. So taking the derivative, so this thingy looks like 2x, and dx dt is negative sine t. So far with me? Plus, mechanically it's very easy to do. This thing is, oh, this is 4x, because there was a 2. And then 2y, and then taking a derivative of this thingy becomes cosine of t. So far with me? Now having said that, this makes no sense, right? Because you have x, y, and t mixed up. So how do we simplify this? Remember, x is this, you get it? And y is this. So you substitute that thingy. So you have negative 4 cosine t sine t plus 2, and y is sine t, and then cosine t. You get it? You get it? So in total we have negative 2 cosine t. And then of course you do remember this is same as negative 2 sine 2t, eh? Ha, beauty, sinusoidal function as we expected. You get it? So at any t value, this thing tells you the slope of this curve.
Wait, I believe it's a negative sine of 2t.
Did I not put negative sign? I did.
Oh wait, no. I don't think it's negative 2. I think it's just negative 1.
Oh my God, yes, you're right. You're right. Like that, huh? Okay. And that thing, you picture-wise, this picture is very important. Although you can just memorize it and do it without realizing what you're doing. But this is the slope of this thingy at any t value. You get it? How about that? Now, this is kind of what I taught you yesterday, but another example. So we have to find dz over dt with a chain rule when t is equal to 0. Okay? So let's try to remember what this was. dz over dt. It went like this. Partial of z over partial x, because see, what we can do is we can substitute these things in here and here and do it, but that's right? So that's not the point. We want to practice chain rule. So we take a derivative, and this becomes dx dt plus partial z, partial y, and dy dt. Okay? So if there are two variables, there are two different chain rules. Good? Okay, let's try to plug it in. So this partial z, partial x is 2xy. So far so good. And then this thingy is just 3y to the fourth, right? Times dz, dx dt. You know what I'm saying? So 2 cosine 2t. You with me? You with me? Okay. Mechanically this is easier, but if you don't know what you're doing, and then if you haven't been doing homework, then you can get lost in this simple problem. So now partial with respect to y. So first one will be x squared plus this will be 12 xy cubed. Still with me? And then dy dt. So this becomes negative sine of t. You with me? You with me? Okay. Now we are plugging in when t is equal to 0. Good. So at t, we can plug this. Usually, if you have to find the derivative with as a function of t, then you have to take this thing here and substitute it for x, and take this thing here and substitute it for y, which is ugly expression. But whole point is we want to evaluate. You have a numerical derivative when t is equal to 0. Let's try to evaluate what x of 0 is. X of 0 here is 0 now, isn't it? That's very nice. And what is y of 0? That's 1, isn't it? So whenever I see x and y, I'm going to substitute 0 and 1. You know what I'm saying? So let's see what happens. This is 0. You know what I'm saying? This is 1. This is 0. This is 0. So the entire second term dies. Besides, t is equal to 0 here, so we really don't have to bother. This whole thing dies anyway. You know what I'm saying? So only thing that has left is this is 3 and this is 2, because this becomes 1, right? This is 0 anyway. So what we have is 6. How nice was that, hey? You get it? Okay, now let's take a little more complicated example. Implicit derivative. You remember forgetting implicit derivative? Yeah, we can still do the same thing, okay? There's no xy as a parametric, it's just a pure implicit derivative. Okay, so we are first differentiating with respect to x, okay? So this thing with respect to x is 3x squared, plus this dies because we are holding y as a constant, and this is plus 3z squared and the chain rule, So we have partial z, partial x. Are we good? Are we good? Okay. Now, and this is a product rule. Okay, because this is y is a constant at the moment. This varies and z varies. You know what I'm saying? So we'll think of this 6xy as a u and this z as a v. Okay. So 6xy, this is a u. So u prime is 6y. And then v, which is z, good, plus 6xy, u, and v prime is partial derivative. The other side becomes u. Are you with me? So we can solve for partial z, partial x. Too much algebra, so doing it in our head, x squared minus 2yz over z squared plus 2xy. How about that? You and me? Too much algebra? Can you handle it? Likewise, what about in terms of y now, right? Well, very similar. This dies, so this becomes 3y squared plus 3z squared partial z partial y plus, now this thingy, once again, 6xy is u and the other one is v, so we have 6x now and z plus 6xy and partial z partial y. So we get very symmetrical result. This thingy is equal to negative y squared minus 2xz over z squared minus 2xy. How about that? Good.